Welcome back, AP Stat. This is the second part of the discussion on random variables. And we're going to be talking about variance and standard deviation. Last time we talked about expectation or the mean. Now we're talking about measures of spread, variance and standard deviation. So the measures of spread we learned about earlier in the course, namely variance, which for populations is sigma squared. For samples, it's s squared. And in this lesson, we're going to see, since we're talking about random variables, we would just see VAR for variance, and then whatever random variable is there. It's usually x if we're just speaking generically, but whatever letter we choose to use, there it is. And standard deviation, sigma for populations, s for samples, or since we're talking about random variables, SD for standard deviation, and then whatever the random variable is. So variance and standard deviation can be computed for a random variable. So not only do we know using the expectation or the mean what value on average the random variable is going to give, but we can also say something about how variable the outputs of the random variable are going to be. So the variance for a random variable is the sum of what is happening in here. It's the squared deviations. And a deviation is value that the random variable can produce minus the mean that the random variable will produce. We square that and we multiply that by the probability of this event happening. And then when we sum all of these products here, we get the variance. So if you recall, the variance is the average square distance that an output is going to be relative to the mean. If we square root that, we get the standard deviation. So recall that for the expected value for the payout for an insurance policy, it's $20. All right, that was the expectation we came up with in part 1 of this chapter 15 series. An insurance policy may charge $50 per month for such a policy and make on average $30 a month. However, how variable is this policy going to be? Would a couple of big payouts put us in the red? All right, so let's find the variance and standard deviation for the payout for the insurance policy. Yeah, the mean is going to be $20. We expect on average $20 per person buying into this plan. So we would be averaging $30 of profit. But if this is a really random variable, then we might want to charge a little more because we don't want to go under because of an unnatural number of people facing death or disability and requiring payouts. So let's find this variance and standard deviation. The variance is going to be all of this right here, which totals to 149,600. And the standard deviation would be the square root. Now, of course, I would be remiss if I did not describe what on earth is going on. So let's start with this first term right here. This 9980 squared. Where does the 9980 come from? Well, that's $10,000 payout for death minus the mean. That would be a deviation, all right? Deviation from the mean, which would be 9980. I would square that, multiply it by the likelihood of attaining such an unfortunate deviation. Then 4980 I get from the disability row. 5,000 minus 20 is equal to 4980. And then, of course, neither would be 0 minus 20 is negative 20. Negative 20 squared, whether 20 is negative or positive, it doesn't matter. Any deviation accounts for positive variation, which is interesting. Doesn't matter whether the deviation is positive or negative. Any deviation, whether positive or negative, means positive variation. Interesting. And I'll let you think about why that's true. So we have almost certainly this is going to be the chance. Almost certainly would be the chance of getting this deviation right here. However, these values are so doggone high that we would end up with this massive variance, which translates to a massive standard deviation. So there is uh, a real chance that with a few too many of these popping up, that we're not going to be in the black. We're going to be in the red if we're only charging $50 if the mean payout is $20. We got to think long and hard about this. This is one of those times, though, in which your calculator becomes your very best buddy, because we can do what we did on that last slide entirely on the graphing calculator, and it is quite easy. If you're given the numbers this explicitly here, the formula is not terribly difficult to work with. However, the calculator makes this whole process a breeze. So we can find the expectation, variance, and standard deviation for a random variable by entering the possible outcomes of the random variable in list number 1, entering the respective probabilities for each outcome in list number 2, and computing one variable stats. All right, so for new calculators, we're going to make sure we set list to list 1 and frequency list to list 2. Now, for old calculators, you got to remember a little more. You're probably used to this at this point. You go to one variable stats, and you would have to say list 1 comma list 2. We have 2 arguments possible, at least for what we're concerned. I'm not sure if there could be more arguments. Someone correct me in the comments if that's the case. But for one variable stats, you have the list we're referring to and frequency list, which is the likelihood of each of the events in list 1 happening. So one thing to note, the calculator is going to say X bar instead of mu or E of X or E of the random variable when computing the expectation. It assumes a sample even when you shouldn't. Be sure to write mu or E of X or E of whatever the random variable is in your work. Don't just write X bar because the calculator says so. So here we are at the graphing calculator. I've entered my possible payouts, including no payout, in L1, and the likelihoods of each payout in L2. Now I'm going to go to stat. I'm going to go over to calc. I'm going to go to one variable stats, and I need to make sure that list 1 is my actual list of payouts, and my frequency list, which is the likelihood of each of those payouts in list 1, is list 2. If you don't have it there, just go second, list 2, bada bing, bada boom. Go to calculate, and bam, we have our mean, which, as I warned you, they give X bar instead of E of X or mu for population mean. This should be a population mean here or an expectation. So just ignore this notation right here. But we do have correct notation down here. The standard deviation for the random variable X is, as we got, 386.78. If you were to square this number, you would get that 149,600, I think it was, number for the variance. So there you have it. Here we are back at this Lucky Lovers restaurant discount problem. So here's the probability model for the Lucky Lovers restaurant discount. So if we got an ace of hearts, as you recall, we would get a $20 discount, $10 discount for an ace of diamonds followed by an ace of hearts, and then for any other ace we get no special deal. Bummer. So we found that couples can expect an average discount of the mean is $5.83. So the question is, what is the standard deviation of the discounts? How variable are these discounts? Choose your method, choose your quest. You can either do this problem by hand, as it were, with aid of a calculator, or you could just use your lists and go to town. Figure out a method, try this one on your own, unpause the video when you are done. Okay, hopefully you've been satisfied with the quest you have chosen. I'm going to show the longhand method, and just know that if you were to enter these values into list 1, the 20, the 10, and the 0, and the respective probabilities in list 2. By the way, if you didn't know this, you can just enter fractions into your lists and the calculator will convert them into decimal because the calculator is just nice like that. So whichever way you did it, you'll get the same answers, but I did it longhand here, found each of the deviations, wrote them all out like that, squared them, multiplied them by their respective probabilities, found the sum, and that's going to be $74.31 approximately. And if we were to find the standard deviation, just take the square root, it's about $8.62. All right, so one more problem for today's lesson, and this is hands down my favorite problem we've done so far regarding random variables. So as the head of inventory for No Way, nice pun textbook, computer company, you were thrilled that you had managed to ship 2 computers to your biggest client on the day the order arrived. You are horrified, though, to find that someone had restocked refurbished computers with the new computer in, they refurbished computers in with the new computers in your storeroom. How dare they? The shipped computers were selected randomly from the 15 computers in stock, but 4 of those were actually refurbished. Oh no. So if your client gets 2 computers, 2 new computers, that is, things are fine, hunky-dory. If the client gets 1 refurbished computer, it will be sent back at your expense. $100 and you can replace it. However, if both computers are refurbished, the client will cancel the order this month and you'll lose a total of $1,000 for this rookie mistake someone else made. So, what is the expected value and standard deviation of the company's loss? Well, to solve this problem, we're going to have to consider all the ways this scenario could go down. So we're going to use a tree diagram. So here is the textbook's tree diagram. We can check this out. We're going to let the random variable x be the amount of loss, right? So in the unfortunate case, we have a refurbished for our first laptop and the refurbished for the second laptop. That'd be a 4 in 15 chance of having the first laptop be refurbished, and then we would be down 1 refurbished laptop and 1 laptop in total, which means there'd be a 3 out of 14 chance that the refurbished, that one of the refurbished laptops would be chosen again. All right. Those odds would be 4 out of 15 times 3 out of 14, which is a little north of 5.5%. We could then pick a refurbished and then a new, followed by a refurbished. But those are technically different scenarios, all right? Because there are 2 different laptops. And so if we consider the first to be, say, laptop number 1 and the second to be laptop number 2, there are 2 different ways that we could get 1 refurbished and 1 new. And each of those would be 4 out of 15 times 11 out of 14, in which any order you'd like, which would be a probability of 20.95%. Then the most likely event by far is 2 new laptops, and we have save face, and that's going to happen a little over half of the time. So here we go. Let's take all 4 of these scenarios and find the expectation and standard deviation for our loss. Okay, so we have 2 refurbs, so that's going to be $1,000 of loss. The odds of that are quite slim. 1 refurb is going to be $100 of loss. That would be the probability of first new, second refurbished, or first refurbished, second new, which each of those could happen a little short of 21% of the time. And the most likely event would be 2 new laptops is 0.524. So at this point, we have a set of outcomes and a set of likelihoods of those outcomes. The toughest part of the problem is now over. Now all we need to do is put this information in the calculator, compute the expectation, and the standard deviation. So let's hop to it. We have our possible outcomes of loss in list 1 and the likelihoods of each possible loss in list 2. We would go to stat, we would go to calc, we would go to 1 variable stats. Settings are already there from earlier in the lesson. In case you lost them, our list of actual outcomes is list 1, and the likelihood of each outcome would be listed in list 2. And we hit calculate, and bada bing, bada boom. Our average loss would be just shy of $100, $98.90. Standard deviation is quite big. This could go very badly if we're not careful. But the mean is about $100. It could vary quite a bit though. So we got to be careful and make sure that we take care of our laptops.